Deep in the heart of these massive industrial plants, there's a silent network of pipes standing guard. It's a safety system, really, designed for a disaster that everyone hopes will never, ever happen. Today, we're going to dive into the critical engineering behind that very network, the lifeline that protects people and equipment from catastrophic failure.
Okay, picture this. Inside a reactor, the pressure is climbing, and it's climbing fast, uncontrollably. Every second, it's building higher and higher. The alarms are just screaming. So what is the absolute last line of defense? Well, it's not a person, and it's not a computer. It's a pipe.
But this isn't just any old pipe, right? It's a carefully designed, precisely calculated escape route for all of that dangerous pressure. You can think of it like the emergency exit for a building, but this one is for immense volumes of high-pressure gas. Its one and only job is to work perfectly when everything else has already gone completely wrong.
So, how in the world do engineers design this lifeline? Well, we're going to follow their process. We'll start by imagining the worst possible day. Then we'll map out the path to safety, calculate its size down to the millimeter, figure out how to control the violent forces inside, and finally, see how we turn that design into a real-world guardian.
First things first. Before you can even begin to design a solution, you have to understand the problem in its most extreme form. And for engineers, that means anticipating every credible thing that could possibly go wrong.
I mean, that's the real challenge here, isn't it? You're literally designing for failure. Engineers have to consider all these different, unrelated potential problems, but not totally impossible scenarios. The industry standards call this avoiding double jeopardy. Basically, you don't design for a fire to happen at the exact same moment a power failure strikes, unless one could cause the other. You design for the single, worst credible event.
And believe me, the list of potential causes is long. Standards like API 521 lay it all out. Engineers analyze everything from a simple blocked outlet to a major power failure or even an external fire engulfing the whole unit. They calculate the amount of stuff that needs to be released, the relief load, for each scenario, to find the one that requires the biggest escape route, and that one becomes the basis for the entire design.
Now that calculation, it's incredibly complex. It's not just about volume. As all that pressure gets released, liquids can instantly flash into vapor. Their density can change dramatically, and the temperature can just plummet. So engineers use charts like this one to model that behavior and figure out exactly how much fluid needs to escape and how fast it's going to be moving.
So, once you know how much needs to get out, you have to design the path. And the physical layout of the piping isn't just about connecting point A to point B. No, it's a critical safety feature all on its own. There are some fundamental rules you just have to follow. You keep high and low pressure sources in separate main pipes or headers so they don't interfere with each other. You have to slope every single pipe so that liquids can't get trapped and create a blockage. An individual line should always enter the main header from the top, kind of like an on-ramp on a highway, so that any liquid flowing in the main pipe can't back up into a relief line. It is all about making sure that path is always clear.
And now we get to the core of it, the calculations. Sizing the pipe is this critical balancing act between physics, safety, and of course, economics.
Okay, the single most critical factor here is something called backpressure. Think of it as a force pushing back against the safety valve, trying to keep it shut. Now, it's made of two parts. First, you've got superimposed backpressure. That's the baseline pressure that's always just sitting there in the discharge system. Then, when the valve opens, you get built-up backpressure, which is created by the friction of the fluid itself as it's rushing through the pipe. If the total of those two gets too high, it can literally stop the valve from opening properly, a total disaster.
So getting the size just right is absolutely crucial. If the pipe's too small, that back pressure skyrockets and the whole system could fail. But if it's too large, it's just incredibly expensive and wasteful. And here's a key detail. Engineers have to size the pipe not for the expected amount of flow, but for the valve's absolute rated capacity. That's the maximum amount of fluid it could ever possibly release. You have to design the escape route for the biggest crowd imaginable, not just the one you expect. Beyond back pressure, there is a hard speed limit. The velocity of the fluid has to be kept well below the speed of sound, or Mach 1. Because as you approach that speed, you start to get shock waves and extreme turbulence inside the pipe itself. To prevent this, industry standards recommend a very strict limit, typically around Mach 0.7, just to build in a critical safety margin.
And that speed limit brings us to the violent side effects of one of these relief events.
When you force that much gas through a pipe that fast, it gets incredibly loud and incredibly shaky.
The technical term you'll see in the standard is acoustic-induced vibration fatigue failure, and that just brilliantly illustrates the danger. It means the sound, the acoustic energy of the gas rushing through the pipe, is so powerful it can literally shake the pipe until the metal gets tired and just breaks. The system can destroy itself from the inside out.
This chart shows you exactly why that Mach 0.7 limit is so important. At normal subsonic speeds, the sound power is, well, it's manageable. But as you get close to sonic velocity, it increases dramatically. And check this out. At a branch connection, where one pipe joins another, that noise, and therefore the vibration, can spike to extremely dangerous levels.
So how do you tame this beast? Well, engineers use a bunch of different strategies. They can use thicker pipe walls to withstand the shaking. They can specify special low-noise valves. And, this is a big one, they design smoother pipe connections. Using a sweeping, curved entry instead of a hard 90-degree angle makes a huge difference in cutting down the turbulence that creates all that destructive noise.
All right, so you've got a perfect design on paper. It's useless if it isn't built correctly. The installation phase has its own set of critical challenges to make sure the system actually works the way it was designed to.
That pipe is going to expand or shrink violently as super hot or freezing cold fluid suddenly blasts through it. So it has to be supported with enough flexibility to allow for that movement. At the same time, the sheer force of the fluid whipping around a bend creates immense thrust. We're talking like a rocket engine that has to be anchored to the plant structure. And of course, every single calculation, drawing, and decision must be documented for the future.
And that right there is the whole journey, from a potential disaster to a robust, reliable safety system. It's a silent guardian, a network of steel designed with incredible foresight and precision that stands ready 24/7 to provide that one, single, all-important escape route when it is needed most.
This entire complex system is designed to be invisible, to hopefully never even be used. It really makes you think, doesn't it? What other pieces of invisible engineering are out there quietly keeping our world safe every single day?